Hello, I'm Jon Wicks, and in this webinar I'm going to provide an introduction to the world of 1 and 2D flood modelling. I'm going to start by explaining some of the reasons why flood modelling is important. I'll then introduce how you undertake both 1D and 2D modelling, and then talk about where and when 1D and 2D methods are appropriate. I'll then talk a little bit about linking 1D and 2D modelling together, say something about the data requirements, and then finish looking at some of the alternatives to 1 and 2D flood modelling. Through the presentation I'm going to use Flood Modeler to help provide examples of some of the information, and on the screen at the moment there's a screen grab of Flood Modeler with, in this case, a 1D flood model shown. So why do we want to undertake flood modelling? It's because flood risk management activities involve a range of interacting activities. Now the diagram on the right on the screen here shows some of these interactions between these flood management responses. For what we're going to talk about now, let's focus in on those coloured squares on here. The assets, flood incident management, property level, spatial, community engagement and natural flood management. And let's talk a little bit about how flood modelling is required as part of the processes of implementing some of those types of responses. So starting at the top with the flood incident management. So flood modelling informs the derivation of the flood warning areas and also is a key part of the process of flood forecasting for predicting water levels to issue warnings. Moving on to assets, now these may be active assets such as barriers and sluices, or passive assets such as flood defence walls and embankments. Now flood modelling is very important here through many phases of the process of appraisal and design of such schemes, and for example could be used to help set the crest levels for flood defence walls. Moving over to property level responses. Now again, flood modelling can be useful here in assigning which areas it's appropriate to put property level responses in, and also help defining the types of levels you may need to put these in at. Moving on to spatial planning and development management. Flood modelling and flood mapping is really important for zoning the floodplain to help guide appropriate development into the right areas of the floodplain. To raise awareness and improve community engagement, flood mapping is also very important, particularly on the community awareness raising to help people understand whether their properties or their routes to work or whatever it is are within areas at risk of flooding. And then down at the bottom in natural flood management, flood modelling can also be used to help assess the benefits and identify the most appropriate types of natural flood management options. So as you can see, flood modelling informs lots of these options that make up some of the portfolios of measures to try and manage risk. The general flood modelling process is shown on the screen here, where we start by thinking about what is the most appropriate approach for a particular issue we're dealing with. We go ahead and obtain data and build our initial model. We test, calibrate and validate it. Then we go on to the production runs and quality control our outputs. Now this presentation is really focusing on that item number 1 there, selecting the best modelling approach, and that is it's quite a complicated part of the process really. There's lots of things that help you decide what is the best approach to use, and some of those are shown on the right hand side here in terms of looking at the objectives of the work you're trying to do, whether it's for flood warning or for calculating defence levels or something like that. You also need to understand what are the flood characteristics, whether it's a steep channel or a flat channel, whether it's to do with breaching, what type of routes the water will be taking once it gets onto the floodplain. Then the other thing that's helping you decide, the other sort of type of things that are helping you decide the best available approach, is the skills of the team you've got working on it, the data you've got available, what software you've got or can purchase, the budget you've got to undertake the work, and then the timescales you've got available to undertake the work. And all of that can help guide what is the best modelling approach for a particular scheme. Now, a key part of that deciding on the approach is deciding whether you can do 1 or 2D modelling. So let's start by just explaining a little bit about what 1D modelling is. Well, 1D modelling generally refers to solving what's called the one-dimensional equations of flows and channels, and these equations are things that look at the conservation of mass and conservation of momentum. And when you're looking at these 1D equations, essentially you've got a single water level, velocity and flow rate calculated for each cross-section or node in the model. that's for the river parts and the channel parts of it. Then there's also a great range of other features on the in the river and perhaps potentially on the floodplain that you may want to include, and you can model these using 1D equations for these point features. Now there's a great heap, great potential, a large number of these features that could be included in a particular scheme or a location you're trying to do the work. On the screen at the moment you'll see a mass of many different sort of building blocks, 1D representations of features such as weirs, bridges and sluices. The ones on the screen here are the ones that come with the Flood Modeler software. Other software also has these sort of building blocks in there. Flood Modeler's got a particularly wide range of building blocks. It's easier to represent, to find a one-to-one match between the tools that's in the software and the things you're trying to represent in the real world. Now let's try and show this this 1D approach graphically. So on the screen, we've got a meandering river going across the page here. Now 1D modelling is where we, for the river part of it, where we survey probably a cross-section of the in-bank channel, and that's shown by these brown lines on the screen here that are the planned position of a cross-section of the channel, and then we sort of identify that as a node, and that's what those circles, the filled-in circles on the screen, are the nodes that have got data on the cross-section. And there's a little picture at the bottom left there showing what a cross-section of a river would look like. So that would be an in-bank 1D model where the only information it's got on the river are the cross-sections at those points and the distance between those cross-sections. That's a standard traditional 1D model of a river. Now what we can do, again, but still using 1D approaches, is to extend those cross-sections onto the floodplain and have in effect, it's like an extended cross-section across the in-channel and the left and right bank floodplains. These cross-section lines need to preferably be perpendicular to the main flow directions. That's why some of these have got kinks, doglegs in them. And you see the picture at the bottom of the cross-section, it's now going across the floodplain. So when we do the calculations, we calculate water level that goes across the river and on the floodplains. So that's an extended cross-section approach. Another 1D, essentially 1D approach for modelling the floodplain is to not extend the cross-sections, but to treat the different areas on the floodplain, these 4 grey areas on the screen at the moment, using what are called flood cells, or in flood model they're called reservoir units, and they're representing sort of that bucket storage. So it's water will flow into those grey areas and gradually fill up, and then may reach the same level as the in-bank river level, or may not. And you represent these flood cells using a volume against elevation table. And then on here we've got these red lines representing the top of bank, the sort of crest levels of the river or of the defence, and we sort again in flood model they're called spill units, and we spill water out of the river into the flood cells, or vice versa, it can come back into the river across those red lines. So again, this is a 1D representation, 1D in-bank river section, and then 1D flood cells with spill units linking those through. Now 1D modelling is fast to run, really fast to run. It's good at representing the in-channel water levels and flows, and it's good at representing a lot of these point features like bridges and sluices and weirs and culvert entrances and trash screens and this sort of thing. And for many situations it actually produces good enough estimates of flood extent, or you can calculate depth grids from it as well, to understand floodplain flow and to be used for flood mapping. However, when you have complicated flow routes on the floodplain, it's harder to work with. You've got to try and predefine those routes before you set up the model, and it can take time to do that. And in particularly complicated areas around in urban areas, around roads and around buildings and things, it can produce a very poor representation of those flow routes. Also, there's no velocity distribution on the floodplain, so if you're trying to do a hazard calculation, where hazard means a function of both velocity and depth, it can't really do that very well. You can do it with zoning, but you can't do it explicitly from the approach. So let's move over to 2D modelling. So 2D modelling, now it's solving what's called the 2D equations of flow. So it's the same characteristics those equations are representing, so it's conservation of momentum and conservation of mass, but this time it's solving them in two dimensions, sort of like an x and y, or an easting and northings direction, if you like. There's a variety of ways of solving these equations within Flood Modeler. For example, there's something called the ADI in the TVD scheme. These different solvers are better for different types of things. So ADI is better on the sort of lower slope, lower velocity areas, and the TVD is aimed to capture shocks, so it can do a very sharp front to a flood wave. It's 2D, not 3D, so that means it usually means that it's doing a depth average calculation of velocity on a grid, working on a grid or a mesh. The key data item for a 2D model is a digital terrain model for the floodplain, and if you're also modelling the channel, you need to have full bathymetry of the channel. Now, what would this look like if we take our example bit of channel again? So here we've got the in-bank channel in the floodplain, and here, if we're doing it all in 2D modelling, we would cut that up into either a mesh or a grid and represent the whole thing in 2D. So it may, the calculation domain may look something like we've got on the screen at the moment. So, what are the pros and cons of 2D modelling? Well, some of the good things about it is you don't need to predefine the flow routes. It will calculate the flow routes across the domain using the information within the terrain model and the momentum of flow. It can be very easy to set up a purely 2D model. It can be very accurate. You do get a velocity distribution across the floodplain. And on the right hand side of the screen here, we've got again results from Flood Modeler. In this case, you can see little lines which are actually velocity arrows, and it's showing you the velocities at a particular timestamp. I think in this case, as the water moves its way, in this case from the south of from the bottom of the picture up towards the north, which is the downstream end. And it directly, the methods directly produce the flood maps and the flood depth grids as direct outputs. You don't need to do any post-processing of them. Problems with 2D modelling is it can be very slow. It can take hours and days to run. It's poor at representing the point features such as bridges, weirs and sluices. And if you're modelling the channel in 2D, you generally need a relatively really fine mesh, particularly for small rivers, to capture the what's happening in the channel. And this is, I guess, it's those dealing with those strengths and weaknesses where we've led to a lot of work now being done in what's called linked 1D, 2D modelling. And this takes the best bits from 1D and 2D. So the 1D channel, or rather the channel, will generally be represented in 1D using cross sections and nodes. It could be the way you're going into a wide estuary or something like that. You'd want to model that part in 2D, but generally the river will be modelled in 1D. And then the floodplain, where we want the detail, we model that in 2D, and then we link the two 1D and 2D domains dynamically together, so they're both calculated at the same time. Now, what this would look like in our example bit of river here is shown on the screen, where we've got the channel, the in-bank flows and water levels modelled using 1D with those cross sections where the orange lines are and the orange dots are, and then the floodplain. In this case, we've got the whole of the floodplain modelled in 2D, so we've got, in this case, a regular grid across the whole of the floodplain, and then we need to tell it where to link the 1D and 2D flows, and that's what the red line on here is showing. That will be the link lines linking the 1D and the 2D, or linking the 1D and the 2D model together, and there'll be things set up that tells it to take the water levels calculated at the 1D nodes and look at the water levels in the floodplain and decide how much water flows across the weir type, using weir type equations perhaps along those red lines. That's one way of doing it. The other way of doing it is to mix and match some of these 1D and 2D approaches together. So what we've got here is the same channel. The bottom left there, we want, perhaps as an urban area where we want to use a 2D method to simulate flows across that bit of the floodplain. Then north of the channel, perhaps it's rural areas with relatively simple flow routes and low receptors. We're just going to use extended cross sections in that area because that's nice and easy and appropriate to use in that area. And then bottom right, we've got a 1D flood cell, and perhaps that's a little bit of washlands with a bank around it, and it's appropriate to set that up using this 1D flood cell or reservoir unit in Flood Modeler. So that's explaining some of the an overview of the background to 1 and 2D modelling. So where would you use 1D and where would you use 2D? Well, there's no hard and fast rules in this, but in general, here's some advice on that. But when you're doing flood forecasting, for flood forecasting, its runtime is really important. And generally, well, in the England at the moment, the focus is on calculating water levels at some forecasting points. 1D approaches are very much the standard way of doing it, and I think will continue to be the standard way of doing it for many situations, because it's very robust and very quick and gives you those water levels to help with warning. For flood mapping, over recent years there's been a big move towards 1D and 2D linked models. So the channel itself is modelled in 1D, and then the floodplain generally modelled in 2D, although the actual grid sizes or the mesh sizes can vary depending on how important that particular area is or the complexity of flows. So flood mapping generally linked 1D, 2D models. For operational studies, where you're trying to work out operational routines for movement of barriers or sluices and things, and you want to try many scenarios, and generally you're controlling things to in-bank, then 1D is very much the approach to use there. When you're designing big interventions, then it's probably a combination of 1D and 1D, 2D linked, and it may be that for setting levels, where you're keeping all the water level in bank, the 1D approach is appropriate. But when you're looking at appraisal and looking at residual flooding and this type of thing, it's likely that the 1D, 2D linked approach is most appropriate. Then if we're looking at breach analysis, where we've got holes in defences and things and water flowing out into the floodplain, usually 2D modelling of that breach flow is what's going to be, the inundation from that breach is what's going to be most appropriate. So what are the data requirements? It does vary a bit between whether you're doing 1D and 2D, but here's some general statements here. For the river itself, if you're doing 1D, you just need cross sections, which may be every, 20, 50, 100, 200 meters apart. Whereas if you're doing full 2D of the channel, then you need a full bathymetry. So that's not just at the cross sections, you need everything in between that as well. For these sort of point features like bridges and weirs and sluices, you need the dimensions, you need some sort of coefficients for those, you need operating rules of sluices and things like that. For the floodplain, generally now both 1D extended flood cells and 2D modelling on the floodplain is driven by gridded data, be it LiDAR or other lower resolution gridded data. For linear features, which could be raised roads or embankments, railway lines going through and that sort of things, perhaps you need to capture those separately if they may not be identified well enough in the gridded data. You need to have information on roughness. Again, on the floodplain, you could use land use or land cover information, things like master map, to work out different zones of roughness. And then in the channel, it's usually based on looking at it, seeing what the thing looks like, comparing it to standard values and then calibrating it. The models now need boundary conditions, both 1D and 2D. Usually the upstream boundary conditions are inflows, that's flow against time if you're doing an unsteady model, and usually the downstream boundary conditions are water levels against time or rating curves generated from things like normal depth calculations. You need to start all of these models off for unsteady runs. You need to start them off with initial conditions or initial states. And for the floodplain, you can usually assume that's dry, whereas in the river, you need to have an initial water level and flow in that river. Then when you come to do the simulations, you need to tell it what time to start, what time to finish, time steps, and other sort of optional data to control the run that may be required by the software using. And then as you go through a process of calibrating and validating your model, you need some observational data probably to drive that. And there's lots of types of observational data. It can be just observed water levels from those flows, or it could be flood maps or rack marks and that type of thing. So I focused on a 1D and 2D modelling, so that's the most used within flood risk management, but there are other types. In the past, very much so, physical models were used to try and predict what would happen with certain different flows in different conditions, different scenarios. They still have a very good place in flood management for the design of sort of one-off structures. And for getting into the detailed flow routes around the sides of things that are in the river, then physical models may be appropriate. tend not to be used a lot, really. Then onto the 3D, onto 3D assumptions where you've got layers of water in at a particular point in the domain. You want to know the velocities at different elevations within that flooded column. So this is also computational fluid dynamics, CFD. Now these are used a little bit in flood management, but it's sort of a similar area to where the physical models are used, where you've got one-off features in the channel, particularly where you want to understand sort of complex flows around piers or other features. Then you may need to do some CFD modelling. Not used a lot, to be honest. Then the other extreme is going to much simpler approaches where we're reducing the representation of the physics, so we may be ignoring the momentum effects. And there's a range of simplified methods that are available that tend to be quicker, although they don't always have to be. Are likely to produce, in some conditions, produce good enough results. Others that they're going to be lower accuracy methods, but are good for covering large areas or for in the initial parts of a project. An example of one of the reduced physics methods is the FAST solver that's in Flood Modeler, and the image at the bottom here of the Greenwich Peninsula is for direct rainfall in that area, and we've been able to do to simulate direct rainfall and identify areas susceptible to surface water flooding based on fast runs very quickly. It won't give you information on velocities and won't deal with the momentum effects, but may be useful for particular types of studies. So to sum up, I've been talking about 1, 2 and 3D approaches, and they can all be appropriate, and so can physical models and the reduced physics models. When you're undertaking a study or using results, you need to select wisely, and it can be depending on a range of things, and particularly the objectives of the study and the flood and flow characteristics of the location you're trying to model. At the moment, linked 1D, 2D models are the most used and the most useful. But for many studies, you actually need more than one approach. It's beneficial to have more than one approach applied, and you could have simplified methods at the beginning, 1D, 2D, and then as you go into operational control or forecasting, you should shift back to just using a 1D only approach. And it's much more efficient for the modelling process if you can do all of this using the same data sets and the same user interface. So it's good to have a modelling system that supports multiple approaches, and examples of a system that does that are the Flood Modeler Pro and Flood Modeler 3 software, because that includes 1D, 2D, 1D, 2D linked, and the simpler fast approaches. And with that, I'd like to end my presentation. Thank you.